have Aditya Potukuchi from Rutgers, and he'll be telling us about spectral bound and hypergraph discrepancy.
Okay, so am I audible at the back? Okay, so in general, I plan to present a full proof, so you should just, if you feel I'm lying or saying something that's not very clear, you should just interrupt me in the middle, okay? So this is the topic of the talk I'm giving. So first I'll start by definitions. Hypergraph set system is always a subset of, is a collection of sets of n, and the setting here is, these are colors, right? So think of chi as a coloring of the vertices, and right, so you know the amount of imbalance between these colors of an edge is given by this quantity, right? And so the discrepancy of this coloring is the max over the edges, okay, and the discrepancy of the hypergraph is the minimum, right, is the minimum discrepancy that any coloring can achieve. Any questions so far? So this is the usual hypergraph combinatorial discrepancy. So here's a different way to state it. It's syntactically the same. Just syntactically it's different, but I don't think there's much. So given hypergraph H, just define the incidence hypergraph. So the incidence matrix, as a, so the vertices are here, so the columns are indexed by the vertices and the rows are indexed by the hyperedges, and for a vertex V and hyperedge E, the entry is whether or not V is contained in E, right? And so the discrepancy of H is the minimum. So now these are vectors in 0, 1, minus 1, 1 to the n. The maximum entry, right? So this is the syntactic reformulation, right? Because there's something spectral here for a quantity. I'll just call this lambda is the max over orthogonal to the all ones vector. Okay, so lambda is this quantity. Think of this like the second eigenvalue. So this gives the same kind of crude statistics that the second eigenvalue gives. It will be useful, right? Okay. So right. So this discrepancy is a minimization problem, right? So here's a general hypergraph. Okay. So this is not very important. The other things analogous, pretty analogous. So you want a uniform upper bound on the discrepancy of n-sized hypergraphs, right? First, fix an E, which is an H, and pick chi random. It's easy to see that it's something like of the order square root E, right? Which is essentially, edge can have at most n vertices, and so we know that by throwing away a factor of log n, you can union bound over all the edges. So surely, so this is right. So this is easy. This is easy. So one important result here is due to Spencer in 85. Is actually at most 6 times root n. Okay, so this is a very important. This is a very important paper. This is 6 standard deviation suffice. And so I'm mentioning this because one of the ideas used here is this thing called the partial coloring. I'll get back to this in detail later, but partial coloring essentially means you color the vertices in stages. At every stage, say you color half of the remaining the uncolored vertices, and somehow make sure the description doesn't go much beyond. And it uses this a partial coloring lemma. I guess it's attributed to Beck. I'm not sure when, but yeah, this is attributed to Beck. Right, we'll come back. Any questions here so far later? Any questions here so far? Okay, good. So where's the thing that to erase? So, oh, I'm sorry, I found it. Yeah. Right, so did I miss anything? Okay, so that's that for now. Now we come to a different world. So we call H is T regular if for every V the number of edges containing V is T. Right? So it's T regular. The degree of every vertex is T, and you say H is T bounded. Every is at most T, right? I'll state everything for T regular, but they also work downward. I mean, they work for T bounded. This is the convenient way of stating these things, right? Okay, so here's a different question. So H is again a general T regular hypergraph. What can be said about the discrepancy of H? So does the fact that, is it easier parameterized by T? So that's the question. And there is this so here I guess this is a conjecture. Beck, same Beck. Set so it's actually order root T. This seems to be pretty hard for now. I guess firstly it's independent of n, right? And it's independent, but the point is that so. Again, due to Beck and Fiala, is that so it is, you can prove that it's independent of these things, and as I don't know an easier way to show this, and this is not easy. This Beck-Fiala, and this seems to be the easiest way to show these things, right? Right. So the point is, yeah, you want to improve this bound. Okay, so it's not hard to actually show 2t minus 3. There's more than one way to show 2t minus 3, and this also appeared in a paper of I guess this was a note. Okay, but I'm sorry?
That's a stronger statement.
This is a stronger statement, yes. Right, but
I see. No, good.
yeah, it's a short note. It's not. There's nothing. Like look at this proof and try to optimize it. There's more than one ways to get here. Okay. And I guess the current best known bound is due to again Boris' book. I guess in 16 is right. It's log star t. So there's an obvious joke here, but right. Anyway, but the point is, yeah. So I guess that's one interesting thing about this conjecture. Yeah, I'm sorry.
So for the conjecture, is that known? If it were true, would it be tight? Are there examples of hypergraphs where you do need
Right. Yeah, there are examples of hypergraphs which is tight. Yeah. So in particular, there's examples where this is tight.
And all of them have size n, I guess?
I'm sorry.
And all the edges are like n over 2 regular?
Right, n over 2 regular. But for any t, I mean.
That's always n bounded. Oh,
Sure, it's n bounded, but if you want other bounded, just take blocks of that. So just take a hypergraph which on t vertices, just make independent copies of that. So it's so that's tight. Good. Great. So hard, but okay. So I don't want to erase this part yet. So one problem, no one knows what the real problem is. It could be false for all we know. Is of course by edges I mean hyperedges. The problem, I don't know. So far, one would guess that T regularity, you can have some pretty large edges, and maybe they're the ones that are causing the problem, right? For example, if you have. If it was T regular and T uniform, you can get this if you promise that there are no large edges. Right, and this is, can't find a reference for this, so I'll just say Lova's local lemma. Okay, good. So that's the so this is the current state of the art on discrepancy. Any questions so far? Okay, so okay. So this is a this is a slightly more recent line of work, which was. So could this conjecture essentially be disproved by picking a random T regular hypergraph? So of course, what I mean by random, you fix n and the size of the hypergraph, and think of this matrix which is size of h times n, right? And for every vertex, just pick T edges to be part of uniformly. So you're fixing this, and this was, so this was first considered by Ezra and Lovett in, I guess, 15. They showed that, of course, here you want the typical behavior of these hypergraphs, right? Because otherwise nothing makes sense. So the discrepancy. With probability 1 minus, say, exponential minus t. Okay. So is this clear? Yeah. So firstly, if I told you t was something like log n. Oh, and of course, yeah. So this is always the condition that we'll be working in. I'll tell you why later, at the end. Right. So if I said that t was something like log n, the statement would be trivial. Is that easy to see? Because most edges will have size t. Well, no, sorry. All edges will have size t, and then that happens. By t, I mean around t, approximately t. So really, the problem was dealing with the fact that there will be some edges much larger than others. Of course, now that we have such a statement, obviously there are two problems with this. Firstly, this one, and secondly this one. T needs to be growing. So if any questions? And so I guess it's more or less independently with this work. With high probability. Okay, so they get the correct bound, and in fact they don't even need this condition again, but we'll get back to this later. Provided so not only does thing need to be growing, it needs to be growing at least at a certain rate. Okay. A question? Yes.
So for you, with high probability means that 1 minus little o sub n of 1, like it's going to.
Yes. But the point is, yeah, I could have said T2, but right. Oh, I said this is not needed, but say you are in this condition, yeah, n is growing here, and T is growing at least as some function of n, and then with high probability doesn't matter, it's T or n. Okay, so I guess the whole point of this thing is that for every T with probability 1 minus the law of 1, and this is as n grows. Okay. Again, the way I'm saying it, I'm stating it like it's a constant, but essentially it takes care of the rest of the case, that whatever is missing. Okay. And any questions so far? And in fact, it is more general. Root T plus lambda. This is for so there's not even a probability statement here. Okay, so questions? Of course, the thing is, why is it more general? Is because right. Right. I'm sorry, I kind of let that part go. Right. So lambda is the max over V orthogonal to all ones. This is the incidence hypergraph. M is the incidence hypergraph. Sorry, M is the incidence matrix. Okay, so to justify why I'm saying this more general is that, okay, I should actually for okay. So firstly, this is not written anywhere. The statement is not written anywhere, but I don't know. So it kind of follows from existing proofs. So the one I'm thinking about is by Friedman, Kahn, and Simredi. I guess 89. Again, so this is kind of an artifact of their proof, but I think I didn't even try to prove the statement for anything above, because this is there. Okay. But yeah, I wouldn't be surprised if this was true for everywhere where this thing holds. Okay, and so yeah, now we agree that this is more general. Okay, so in fact I'll just write this down. Right, so the rest of the talk is just the proof of that. And So I guess in absolute terms, this is more difficult because this is not very easy, but the proof of this is not hard at all.
The proof of Bansal and Meka is not spectral?
It is spectral, but yeah, it is spectral based stuff, but it's different from the way. Yeah, and I don't think you can get a statement like this. There is some high probability in there, so I don't think it's a deterministic statement as far as I. Yeah, I'm not 100% sure, but yeah. Okay, the proof of. Firstly, a prereqs. So yeah, I said something about partial coloring right here. Skillfully kept myself from erasing it. So this is a theorem. So this is, I guess, something like the algorithmic version of whatever's happening here. Oh yeah, I forgot to mention. Plus, there exists a polytime algorithm. So everything I'm just doing is algorithmic. Right. Okay. So anyway, so let's start with the partial coloring. So there is an algorithmic version, something like a version of this partial coloring theorem. Okay. So this is due to, again, so the repeating names here. This is randomized. And so recently a paper, Levy, Ramadas and Roth, this is deterministic. Okay, so okay, I didn't even tell you the statement. It's okay. So let H subset of let H be a hypergraph and X naught be a starting point, and let be constant such that okay. So let Ci's be the constant satisfying something. Then there exists in X such that the first point is okay for every E. Okay, the indicator of E means the indicator vector of the edge. This is trivial, like x equals x naught does the job. The second thing is 1 so it's 2 for it. So at least half the vertices get a proper color. So this is what I meant by partial coloring, right? So half the vertices get an actual color. The other half are floating somewhere in -1 1 to the n. But okay, so we call these implies so and uncolored means the same thing. Okay, so usually okay, so let's see. We proceed in stages of partial coloring. Yeah.
So should I be thinking of x naught as being like all zeros vector?
Yeah. So you start off with x naught being all zeros vector, but I guess I need an x naught because after the first step, some vertices have something which is non-trivial. You want to remove that and put a new vector, and you need this in that case, right? So it's. I think it's 0 bar, and it makes.
Can you repeat the coloring, partial coloring?
I'm sorry?
What algorithm repeat how you partially colored?
Oh, I'm using this as a black box. This is a theorem of Lovett and Meka, and so the point is, given some constants, such which satisfy some condition, there is a partial coloring. By that I mean some vertices get color 1 or -1, some get somewhere in between as a real number, such that every edge with respect to this fractional coloring gets discrepancy at most this constant times its standard deviation.
And then how will you iterate it? You'll fix more things to +1 -1 in the next step?
Yes, exactly, right. So let's. So yeah, first think of x0, which is all zeros. Okay. Once you color it, you get half of them 1, -1, and the other half are some real numbers. You have no control. And now when you have to color it again, you have to use the theorem where you want to remove this and replace half of them by +1 -1 again. So you're removing whatever discrepancy you have here and adding this.
So you'll take a sub-hypergraph. These ones will be forever.
Right, a sub-hypergraph, yes. And you kind of this is how right. And
So there's no eigenvectors yet.
no eigenvectors yet. Right.
So when you apply this partial coloring iteratively, you actually apply it only constant number of times?
No.
You apply it some log n number of times?
As long as it goes down, yes.
So then I guess maybe there is some worry, right? Like at each stage your discrepancy rises by some square root of e.
Right,
but
right.
You're doing super constant
Right.
anything, so you can't just
Exactly, right. Yeah. So I'll just good. So okay.
My geometrically decay.
I see. So you tighten the constraints as you go along.
Yeah. Yes.
Okay.
You're thinking this is like a Rayleigh quotient or something like that?
No, there's no Rayleigh quotient. So lambda I'm thinking of as some kind of a Rayleigh quotient, something like that. Yes.
But there's coloring also you could add to the Rayleigh quotient. Yeah, right?
Oh no, I don't know any easy way to describe. No, this is again, this is not easy. This is I don't have an easy description for this coloring.
But every vertex has an assignment, whether it's +or -1 or a real number.
Something in routine, yes.
Well, it doesn't have a Rayleigh quotient, but you're not interested.
Yeah, I'm sorry?
It has a Rayleigh quotient, but you're not interested.
Yeah, right. This works for any, it is independent of, I don't know how to use the Rayleigh quotient to get a better answer
Is
here.
it orthogonal to the old ones or not?
So far, nothing.
Okay.
Is it orthogonal to the all ones? I don't. I don't recall from the proof that I can't recall immediately that
You might
this.
have a full hyperedge and then it might not have discrepancy 0 on it.
Right. Yeah. So, yeah, it's not orthogonal to all ones. Yes, because whatever hypergraph you have, just add the all ones vector below it. Right, so whatever hypergraph you have, just add another edge containing every vertex. So if you cannot have 0 here, then you're not going to have 0 here. So it's not orthogonal to. This is not easy. This is I don't know. But I guess okay. The attention is on CEs. So I can make CE equal to 0. Right? I can have some. I can be orthogonal to some edges. Okay. How many of them? Again, if I make C0, this is 1 for edges. Right, so then it's one of these things that for whatever they were doing, they do mention this, but they don't use it. They said, yeah, maybe it will be useful somewhere, but yeah, that seems to be important here. Okay, anyway, so this is important. Okay, so right. So you're going to color this in stages of partial coloring, right? So at every stage you have the uncolored vertices of the previous stage. I'll just set up some notation for that. So let's say stage I, say I equals 0. Okay. So Vi is the set of Vi is set of uncolored vertices. So I said for at least NO2 vertices, without loss of generality is exactly NO2 vertices. Right? Because I just, even if it has, I'll call it uncolored and push it forward. So this just to make the analysis easier. and EI. Okay, so and this is the remaining part of the edge until you get there. Okay. So now I guess I don't need anything else here. So what is the idea? Like, look at a typical edge. Okay. If this E kind of behaves well, you have, right? So this is the average edge size. So if an edge behaves well, whatever that means, have this. And at every stage, when you color half the vertices, let's say the edge size cuts down in half. Okay. And let's say EI. And let's say we use a constant, say C0, like, and let's say we are using constant C0, C1 for the stages of partial coloring. So you finally get that is something like sum over Ci root EI, which is something like times sum over Ci times 2 to the I minus I. So the point is Ci has to keep growing, because in every stage of coloring half the vertices, this quantity is reduces, but the number of summands are the same. So you have to increase Ci a bit to make up for this, but that's saying nothing compared to what's happening here. That's the hope. But then this has been the hope for every discrepancy paper. It doesn't work always. So the point is, this is where the spectral thing comes in. I need that. Can I, let me use this part. So here's a lemma. Again, it's not hard at all, and I won't prove it. And S is a subset. Right, and the point is, look at the what do you expect the size of this to be? Right, like you take alpha fraction of the edge, you take alpha fraction of the vertices, you cover alpha fraction of most edges. So I guess, suppose I want the number of edges such that this happens. Does this make sense? Is at most say lambda over, it's small, it goes down as as lambda goes down. And I don't know, so this is reminiscent of the expander mixing lemma. I guess which is slightly more household. Right, the point is that you take an alpha fraction of vertices, you cover an alpha fraction of most edges. And how many of them deviate depend on the second eigenvalue. Right, and now
so here T is the size of the edge?
yes, the size of the edge. No. T is the regularity. Yeah, the degree of a vertex. Oh, I should have said T regular. Look, this is just some parameterization. I could have put anything here.
No, I'm just saying what the expectation would be, right? So if you
The expected
for universal for, I mean, if you think of a random S, I figured the expectation will be alpha times the size of E.
right.
And you have alpha T there, so I got confused that when the size of E is
alpha
T.
E, I think. Is alpha times the size of E?
No, but you put T there. Right?
I put but T is some parameterization again. Like if you use Markov, for example, I mean this is second moment bound. That's the point here. So an average edge has size alpha E and is unlikely to deviate. But the point is the number of edges that
So
deviate.
the expectation is indeed alpha E, so this is just the deviation. So
Right.
it doesn't matter.
And the deviation.
Parameterizing, okay, never mind.
Right. You are getting a second moment deviation here. That's a. Okay, so from now on it's just flushing out the details. Okay, there's a clock there. Okay, good.
Just to clarify, we still assume that we have exactly n edges, right? For this, the number of hyperedges here is n, or does that not matter for this statement?
Doesn't I want to say doesn't matter, but you have at least n hyperedges.
At least n.
At least n. Yeah, I'm sorry. You need at least n, right? Right. So again, everywhere. I need this. The point is, if you have more than n, the average edge size is only smaller.
Yeah.
Okay, good. So, so questions so far? So this is the thing. From now on, it's just fleshing out the details. So let us set D, I guess, dormant. Again, we are in stage I. And so all we have to do is come up with a procedure of what to do in stage I, and then there's something to analyze there. Okay, so the edges that are too large at stage I are dormant. So of course, not dormant means they are live. And let's B call the bad edges. Let's say 10 lambda. Okay. If an edge was, again, like I said, if it behaved well, EI should be 2 to the minus IE. Okay, and it's bad if it deviates a bit from that. And of course, not bad means good. And
So just to make sure, that lambda is the same as the...
yes, this lambda is the same as that lambda, yes. And dead. An edge is dead if okay, let's just say that if it gets too small, you don't have to worry about it anymore. Whatever you do at this point, it's going to get discrepancy at most lambda. Okay, so okay, I don't feel like erasing any part of this. Okay, I'll erase this part. I'm sorry? Oh, can I?
Yeah, you can just move.
That moves, that podium.
Yeah, that small podium moves.
Okay, sure. I guess, yeah, that's not a problem. If I can. Okay, so the main point is that firstly, the size of what is the yeah, D is at most okay. This is an averaging argument. And is also at most 2 to the minus I over 100, right? And this comes from this bound, right? And so you realize that this is so all the bad edges, which are very few in number, I can set Ci's to be 0 for all those bad edges, for all the bad and dormant edges. Right, and from there it's so all we have to do now is figure out what the CEs are, and I'll just list them out. For E, if it's bad or dormant, is 0, right? If not, again, before I state anything, I'll just use a bit of notation. Let AJ such that EJ okay, let's say this is visible. Okay, Is this okay? Okay, So what happens to an edge in AJ? Suppose it's good. I mean, you can be dormant and bad too, but suppose it was good all throughout. For J steps, it's going to get CE0, okay, based on this. And then once it's live, you can start charging it for discrepancy. So once it's live, so for again, these constants, I mean, yeah, just because I have to say it. This again only makes sense if I is at least j. Okay, otherwise it's 0. So as long as it's dormant, it doesn't have to pay anything for discrepancy. But once it's live, you can start charging it. And all I have to show is that this holds. So and yeah.
AJs are all dormant? No.
AJs are just the subset of H that have size something like 2 to the j to 2 to the j minus 1.
How do they relate to the dormant?
Right. So they will be if they are good, they will be dormant for j steps. Because every time the size cuts in half, in j steps you'll expect that the size of this gets less than 100t. So
Dormant for all the guys who are bigger than 100t?
yes, dormant for all the guys who are bigger than 100t at stage I. Right, does it make sense? So
I think the thing is that AJ is the set of edges that you expect to become not dormant in about j steps.
So
right.
It's a refinement of the dormant set.
No, a dormant is defined for every stage. AJ is a subset of the hypergraph.
Okay.
And AJ, you expect them to become live after j steps. And right, I guess I'll quickly show I don't need this anymore.
Like AJ is defined with respect to VJ, right? So which is something.
No. AJ is not with respect to VJ. AJ is just a set of edges that you expect to become dormant in j steps. AJ is a subset of the hypergraph, not of the jth.
So what does E sub j mean?
That'd be like,
Oh, sorry.
Oh, great.
Oh, I'm sorry. Yeah. Oh,
that'd be like
Right.
minus j minus 1 minus j. It should go down.
No. These are the big edges.
These are the big ones.
These are very big, and after j steps they become normal size. They become
Now I understand. Good.
right. I'm sorry about that. Yeah.
So initially it's you're taking all
So
the
they
dormant
start
guys, you are kind of breaking them up into when will they become
Exactly.
dormant.
Right.
That's your
Right. And the idea is the following. Yeah. So you can only charge this thing after j steps, and once it wakes up, you can start charging it normally. But for CE. Okay. And now I'll just first. Okay. I'm skipping a few steps here. Okay, all the bad you get 1. You're gone there, and summation over all j, summation of E. In fact, right. No, I should. Okay. The point is that averaging. Okay, and so this is at most 2 to the minus j, and again this 4 and 2 were chosen so that this happens, and so this is essentially g is less than I. Which is at most 1. On the other hand, this is And so, yeah, sure. It's clear, right? This holds. Right, and let's see. Yeah, so I guess both are justified. Root t is justified because, yeah, I should say this. So here I'm going to list a tiny bit, but it's not that much at all. Let's compute the discrepancy of an edge until it becomes dead. Okay, so it's only ever has discrepancy once its size gets less than 100 root t. So this is upper bounded, and which is at most 2 to the minus that's what's happening, right? That's what's happening, right? And so it's just essentially order 2t. And once it's dead, you have no choice but to give whatever is left. And so this is where the root t comes from. This is where the lambda comes from. And I'm saying that's the end of the.
But that explains the root t. But how does the lambda part come?
This is until an edge becomes dead. So once it's dead, you no longer half at every stage. Plus, you have some discrepancy that you've accumulated from whatever x gives you there. Any questions? This is the full half of the proof. Because yeah. Okay, so there's no questions. I'll move on to some.
So at a high level, the dead was when the size of the thing becomes less than lambda, and then you just stop.
Right, but because then this expander mixing lemma gives you nothing. Right. You no longer have this halving at every stage. You just throw away whatever you have.
And then until then, you were kind of saying that look, you are going to be every edge is going to be kind of halving every time.
Right.
And you had this somewhat careful sort of stratification of these sets into when they'll become alive and how much they can take a charge.
Right. Right. Yeah. So exactly. Yeah. So just.
And then those edges which were not covered by the expander mixing lemma, I guess somehow
They keep getting 0 until they get small enough. I mean, they have to be small enough at some point. Okay, so I'm done with all of it. So I'll just reduce a bit. And okay. So yeah, I promised to talk a bit about. We promised to talk about what happens if there are too many vertices compared to edges. If suppose n is bigger than h. And by bigger, I mean much bigger. Because everything, I mean, I didn't need h's less than n. I just needed to be like omega of. So again, so there's a bunch of. So I guess. I should again take the chronology properly. Again, the same paper of Ezra and Lovett I mentioned before. They say that if n is m to the t, sorry, it's to the t, okay, this is extremely dense, then so it's random. So the point is that so far, I guess random is kind of trying to get around the fact that we can't solve the full conjecture. But as n becomes larger, you can start some interesting things happen.
Wait, is n the number of vertices?
Yes.
So you're saying there are way more vertices than n?
Yes.
Isn't that sparse?
Yeah. I'm sorry?
Wait, if you want like dense, don't you mean the number of hyperedges to be like roughly n to the t, like almost all possible t subsets are there?
Right, these are extremely sparse. So.
Oh, sorry, because I said dense. Okay, then I misunderstood. Sorry, you're thinking of them as sparse.
So, I don't know what dense and sparse means. I mean
yeah,
that.
okay. Sure. Oh, you're saying okay, sure.
So because the point is that the edges are very large.
I see.
That's
Yeah.
the. Right. So you get this kind of stuff, which is not really given by the Beck-Fiala conjecture. So, and I guess I should say again, Franks and Sachs. That n is, I guess, it's t, right? T is pretty bad. So tilde. I don't remember where the log goes, numerator or denominator. Cubed. Then you get that discrepancy which is at most, I don't know, 3, 2, something like that. Yeah, it's at most 2. Okay, so I'm conjecturing. So if there exists a C such that n is bigger than Cm log n, implies is 3. This actually is big O of 1. Let's just keep it like that. And why? What is the point? The thing is that very interesting things happen if you have too many vertices. So both, I don't know, I can't recall the proof of this, but the proof of this goes by showing the following. Here's how your matrix looks. You have way more edges than, vertices than edges, right? So you look at all plus minus 1 combinations of this vector, you have enough that some kind of a limit theorem holds. You should be able to get vectors like things like that.
What's the right hand side?
Oh, I'm sorry.
Oh, no, I was just wondering what the right hand side was.
It's something like, it's at most like plus minus 2 vectors.
Okay, yeah.
So you take a lot of random looking t-sparse vectors, you take all their linear spans, and their average is something like 0. So you should expect most points around the mean get a lot of weight. And I guess a slightly easier version, okay, I did not really intend on plugging this, but this is all for random t-sparse, right? So what if I picked every incidence independently with probability t over n? There it's slightly easier. Again, kind of independently and.
But what is known in the ratio of your conjecture? Is it known that it's at least O of root t?
Yeah, because Bansal and Meka, if t is large enough, right? For small t, I have nothing. Yeah.
So in the direction of the result, let's say like n is n log m or whatever.
Right.
Then what's the best bound on discrepancy we know?
Random?
Yeah, for a random age.
Nothing. If t was large enough, you have that it's.
So in this regime, there's basically nothing, no?
In this regime?
Yeah.
Yeah, for a constant t, no. Okay, because again, that's because it's a more recent. Okay, by nothing, some things are known, obviously, 2t minus.
Yeah, sure.
So again, so here's a matrix, and every point is IID, and so here Hochberg and Rothfuss. I'm saying this because they use similar techniques. They use this kind of local limit idea of this. Let's say that discrepancy again, and they get better parameters. N square, it's not cube anymore, means the discrepancy of H is order 1. Okay, square. And yes, whatever. So they ask an open question, like that was inspired by an open question of here. Suppose you have n is omega of h log n. Let's say, I'm thinking of both of them on the same polynomial scale. So this log h log n doesn't mean anything. And say whatever this Bernoulli random variable is, and t equals n over 2, right? Then yes. Then what is this discrepancy? Is it better than root n, and right. So and there's a preprint that I uploaded some time ago that kind of says that here you get a constant too. So I'm going to say, without being again ambitious, it's an archive, and these local limit theorems don't really come with algorithms. This is a very lengthy second moment computation, so it doesn't have an algorithm too. You get that, it's again it's order 2, sorry, 3. Yeah, I think one of those things, when I uploaded I wrote it as 1 and someone said no, it's actually 2. But okay, yeah. So and for other Bernoulli this kind of similar thing expects like kind of holds, and it's under preparation whatever. But T regular seems to random T sparse vectors. You try the same second moment arguments, it becomes very messy. Not that this is any less messy, but it seems hard. So this is something that is not given by Beck-Fiala conjecture, and I think that's one of the reasons I like this. That's it. Any questions on this? Yes.
Just to throw it out there, is there a hope that this can help towards the Beck-Fiala thing, because you have the spectral thing? Suppose lambda is large, then you find that Rayleigh vector, can that guide you towards some recursion?
So far I could not, but I don't. Yeah, I mean, so that was the hope too. That even if t was order n, you know the answer, right? If t was slightly less than n, like say n over log star n, I was hoping at least there you can expect. It wouldn't be very spectacular, but I mean, not much is known here, and I so far.
So in fact, in that direction, it seems like you only use this expander mixing or analog of the expander mixing lemma on sets.
Right.
So the vectors you are going to invoke it on are 0, 1 vectors.
Right.
So maybe you don't need lambda, you need like the maximizer of mv over v, where all v are Boolean. Is that true? Could you replace?
Yeah, I think, because the condition on the definition of lambda came from the proof of expander mixing lemma. So yeah. I don't think it can't be tweaked at all. Yeah.
But also those are within some log n or something, right? There is some.
But the logs are important here, right? Like it seems like the game is of logs. Otherwise there is Banachek and. But like if you want to lose log n's or root log n's, then root t log n is known, right?
Root t log n is known. Yeah, root t log n is known.
So it's all a game of logs.
And so I guess I have one more thing. Again, so the matrix, it uses the fact that the matrix is a 1, 0 vector, and if for example the matrix at 0, 1 and minus 1, nothing. This is expander mixing lemma says nothing. But for different, because of Komlow's conjecture, you expect the statement to be true there too. And is there any kind of spectral analog of meaningful spectral with does not do squaring the entry, something like that? Yeah, any non-trivial spectral analog of that would help.
Actually, in that direction, is there a version of your result that would work for let's say random t-sparse unit vectors or something?
No, that's what I'm saying. Yeah, so once even not just that 0, 1, minus 1, I have no idea. I mean, sure, maybe you square the entries of the matrix, but that's cheating. I don't know. This has to be with the fact that the matrix has positive entries. So. And this is still open, right? The Komlow's problem for orthogonal vectors. So so that's why the plus 0, minus 1. I have no idea.
Okay, if no more questions, then we can time the